today we are going to learn about the nature of light. So we're going to be looking into ways that light behaves. Our objectives for today: first, we're going to describe the electromagnetic spectrum. Then we're going to define what light is. We're going to spend some time explaining the dual nature of light, how it's both a particle and a wave. And we're going to list and describe how light can interact with different objects based on those properties. So let's start by defining light. What is light? Well, it's a form of electromagnetic radiation. So when we talked about heat transfer and we talked about conduction, convection, and radiation, this is the type of radiation we were talking about. And it's a kind of radiation where electrical fields and magnetic fields are vibrating in a synchronized way. So if you remember from the light polarizing simulation, we looked at how the waves were oscillating up and down, but also side to side. So one of those would be the electric field and the other the magnetic. Light is just one part of the electromagnetic spectrum. It also includes radio waves, microwaves, infrared waves, visible light waves, ultraviolet waves, X-rays, and gamma rays. Okay? So like any spectrum, we're measuring a range of something. So if we have a full spectrum of ages in our classroom, that means we have a large age range, people from many different ages. So when we're talking about the electromagnetic spectrum, what is that range? Well, that range can be in terms of frequency, wavelength, or energy. Okay? So if we are looking, we have a wavelength. We start out on this end with radio waves with long wavelengths, and by the time we get over here to gamma rays, our wavelengths are much shorter, okay? Which we know then means that the opposite is true for frequency. We have high frequencies over here and low frequencies on this side, and that also correlates to how much energy they carry. Waves that have short wavelengths and high frequencies carry lots of energy. You can see that outlined down here for you. And ones that carry little energy are long and have low frequencies. All forms of electromagnetic radiation carry energy, and they all travel through space, and they travel at a specific speed. That is 3.0 times 10 to the 8th meters per second. You might remember that from our calculation worksheet because we talked about it being the speed of light and radio waves in the air. Obviously, when they're traveling through a medium, they're slowed down slightly, but air only slows them ever so much, so we used the same number on that worksheet. Now, light is interesting because it doesn't behave 100% like a wave, and it doesn't behave 100% like a particle either. Instead, it has properties of both. So in the science community, we say it has a dual wave-particle nature. That means in some situations, it's going to behave like a wave, and in some situations, it's going to behave more like a particle. And it depends on the situation which model is more appropriate. And we'll start by looking at the wave theory of light. Light has lots of properties that make it like a wave. It has a wavelength and a frequency and a speed, and it carries energy, all things that make it similar to waves. It also exhibits some of the wave behaviors that we talked about in our first lesson of notes. For example, when it passes through different mediums, it is diffracted. And different wavelengths of light are diffracted different amounts, which is why passing light through a prism can yield us a rainbow. Also, when waves run into each other, they experience interference. We looked at patterns of interference in laser light in our lab. So when the waves are interacting with themselves, then they exhibit some wave-like behavior. But it's not fully acting like a wave. It does have a particle side, and this is primarily related to something called the photoelectric effect, which we also looked at in our lab. So when light is interacting with matter, then it often behaves more like a stream of particles, and we call these particles photons. The best example that we have of light behaving as a particle is the photoelectric effect. When light strikes the surface of a metal, it has the possibility to excite an electron and cause that electron to then be ejected from the surface. It gains enough energy to escape the surface of the metal and be emitted. Okay? But this can only happen if the correct amount of energy is transferred from the light to the electron. If the correct amount of energy is not transferred to excite this electron, then the electron is not emitted. If light was behaving purely as a wave, as we increased intensity, the increase in energy would eventually cause an electron to be emitted no matter what. But we don't find that to be the case. What we find is with different metals, specific frequencies of light cause electrons to be emitted, meaning that the photons, the little packets of energy being transferred by the light, carry a specific amount of energy. And some frequencies are carrying enough energy to cause them to be emitted, and some are not. Also, the fact that the electrons are emitted immediately upon the light striking indicates photon behavior, because waves would require a more gradual release of energy into the matter, which would cause the particles to be emitted eventually, but not immediately. Now let's talk a little bit about how light interacts with different materials. Because light is like a wave and it carries energy, it can interact with materials in several different ways. Okay? First of all, we get reflection. You're familiar with the concept of reflection. Light strikes an object and it bounces off of that object. Okay? Smooth surfaces produce what we call regular reflection. Okay? So you can see how nice and neat these waves strike the material and bounce off of the material, meaning that every piece of information reaches your eye, and it reaches it in an organized and orderly way, meaning your brain is then able to interpret it as an image, an actual picture. So in order to do this, surfaces have to be smooth even at the microscopic level, which is really only done by mirrors, glass surfaces, and some polished metal surfaces allow us to see ourselves in them. If a surface is rough, it produces diffuse reflection. Okay? So you'll see how the light is still being reflected, but because depending on where it strikes is going to affect how it is reflected, then not all of the light is going to reach your eyes, and what does reach it is disorganized, out of order, and therefore your brain can't interpret it as an image. However, the light is still being reflected to your eye, and so your eye can interpret some information, and what it can tell you is what wavelength of light was reflected to your eyes, and that is what our brains interpret as color. So every year I have students who tell me that objects that aren't mirrored don't reflect light. Unfortunately, if that was the case, we wouldn't be able to see those objects. Instead, we would see a black empty void in their place. So all objects reflect light, it just matters how they're reflecting it on whether or not you're going to see an image. Light can also be absorbed, okay? White objects reflect all wavelengths of light, so you can see that visualized down here where we have all of the different colors. And black objects absorb almost all wavelengths of light, okay? So when an object appears black, we're not seeing a wavelength of light that corresponds to the color black reaching our eye. What we're actually responding to when we see the color black is an absence of light being reflected to our eyes. Our brain is saying, hey, this object is absorbing most of it. This is why also that white objects tend to not get hot in the sun quickly, but black objects do, because when that energy is taken in or absorbed, it is converted into thermal energy for us, into heat. So when you wear a black shirt outside in the sun and almost all of those waves are being absorbed by it, it's going to have a lot more energy to change into heat for us than the white object, which is reflecting most of that energy off of its surface. Just like the waves we discussed in our first lesson of notes, when light changes mediums, it changes its speed. Unlike the other waves we discussed, light actually doesn't need a medium to travel, which is fortunate for us because there is not a medium between the sun and the earth. So if it needed a medium to travel, those waves would never reach us. It doesn't, but that doesn't mean it can't travel through them. So it can travel through mediums here on Earth. And when it changes mediums, then it is going to get bent. And we can see a sort of phenomenon we can see because of that, where at the water level, this pencil appears broken because when the light is passing through the air and then the glass and then the water, its speed is changed. It's bent, the light angle is bent, and so the information reaches our brains at different times, and it appears that this object is broken, essentially. We also have transmission. Okay. Some objects are going to allow light to pass through them without doing too much reflection or absorption. So you can see here that some light is still being reflected off of the glass and some light is still being absorbed by the glass, but the majority of the light is being allowed to pass through it. And this is what it means to be transmitted. If an object allows all wavelengths of light to pass through it, then that object is going to appear clear, like water or air or glass. If, however, the object only allows some light to pass through it, specific wavelengths, then it's going to appear a color, and the color it will be is whatever color of light it transmits. Okay, so if you are looking at a stained glass window and different parts of it appear to be different colors, it's because those pieces of glass are only allowing one wavelength of light to pass through them, or the combination of wavelengths that results in that color. Lastly, let's talk a little bit about scattering. Scattering is essentially when light is being reflected off of small particles. So, for example, there can be dust in the air, but there's also just air particles in the air and things like that. And so when wavelengths strike those particles, they can be reflected in different directions, and this causes them to scatter. It's much easier to do this to shorter wavelengths, and it's more difficult to do it to longer wavelengths. So when we look up into the sky, the reason the sky appears blue to us is because the shorter blue wavelengths are being scattered and spread out across the sky. Okay? They are still reaching our eyes, but not as directly, and they're being scattered all throughout. So we perceive the sky as being blue. However, at nighttime, when the sun starts to set and the sun's rays are traveling to us through a longer portion of the atmosphere, the blue is actually totally scattered away, leaving behind the only light to reach our eyes in that sort of red and yellow portion of the spectrum, which is why we get such beautiful red, yellow, orange sunsets. All right, that is the end of our notes.